So Gaussian quadrature, this is what I was working out. So this is a method to integrate. So we did one method called Newton codes. So given n points, in fact there were equi-space points, and we could get quite accurate result, and the order the error was either h to the power n or n plus 1. Right? We did that part, like so examples were trapezoid rule, Simpson rule. So that exercise has been done. So this is another one which is more accurate. So if you recall, so you have integral. So how did we do it? Fx dx a to b. I didn't specify what is a and b. Okay, that comes from the choice of your polynomial. So we expand this. No, sorry, I had to wx fx. It will become clear today why wx is important. So this is approximate, of course. J wj f xj. So we have to choose points. These are abscissas, and this is called weight. So if you choose your abscissas properly, then you can get a very good answer. So if I have n points, 0 to n minus 1, in this scheme you can get accurate up to polynomial which is ordered highest power is 2n minus 1. So suppose I want to integrate something which is good for cubic polynomial like x cube, x squared, x and 1, then how many points do I need? And n is the number of points, okay, n is the number of points, I just need 2. So you can see power of this algorithm. So for this is the standard integration routine which is used in practice. We don't use Newton codes in general. I mean, if you look at the Python's thing, Gaussian quadrature is available. So I'll show you how to use it in Python. So what are xj's? Xj is the roots of which polynomial? So I expand in terms of polynomials, and the polynomials follow this property Lx Lj of actually not less than phi. I use phi I x phi g of x. They are orthogonal polynomials. So delta ij, and it need not be, there could be a factor. Okay, so there is a factor here. There need not be 1. So it depends on the polynomials, and wx is not equal to 1 necessary. I mean, sometimes it is 1, for Legendre it is 1, but it need not be. Alright. So you choose these polynomials, and xj's are roots of which polynomial? Phi n plus 1. So this will have n roots. So I will just do some exercise. In fact, we did that for Legendre polynomial. Let's see, I have those notes. Okay, let's start looking at those notes. So these are Legendre polynomials. Okay, so phi naught. So this is same as what you get for hydrogen atom, spherical harmonics, right? And the theta part is given by Legendre. So this is the first one, 0, phi 0, phi 1, phi 2, phi 3, and phi 2 has 2 roots. So it is the third polynomial. According to this notation, it will be phi n. Okay, according to this notation. So let's just follow the same notation. So phi n has n roots, but I am starting these indices from 0. So it should be clear that this expansion is done up to phi n minus 1 in this notation, and the root is of the phi n. So how does it look like? I just so there is a way to plot them. So there is a function there is a package called special. Okay. So using the special package, which I will just put it share with you. So using that, so it will give you phi of x. You don't need to remember them. I mean it is part of Python. So these are the Legendre polynomials. I didn't plot phi 1, phi naught will be constant. This phi 1, phi 2 is this, x squared minus 1, phi 3 is which one? This one. Okay. So there are quite a few of them, and it is defined from minus 1 to 1. So cos theta is 0 to cos theta equal to pi. So it has very, I mean it has interesting properties using which you can define, we can get the weight function straight from the function. So this is a formula for, so these are comes after bit of algebra. Okay. So these are, so weight function can be computed if I have the derivative of phi n at the roots. So this is a formula, but what is given is table. Okay. So you don't really need you don't need to calculate first hand. Somebody has done the whole, all the lot of work, and you can use this table. So the table for n equal to 2. So I want accurate up to x squared, x cube. Then I should choose n equal to 2. And here the roots are, so these are abscissas. Roots are plus minus this number, and the weight is 1. This I did in the last class, but I am just revising it. So for, if you want 3 abscissas, so these are the 3 roots, plus minus means there are 2 of them, and the weights are given here. So here I have to multiply appropriate weight with fxj. You should pair it appropriately. Okay. I mean you can't simply multiply this root with the value of the function here. So this table you should know how to use it, and you don't need to go back and derive from the first principle the weight. Weight somebody has computed already. So we can get up to 5. So these are the 5 roots, 5 weights, because there are, well basically for these 2 values the weights are equal. It's the symmetry, plus minus symmetry. So this is good up to which polynomial? So which polynomial? So I am choosing n equal to 5. So up to x power 9. So this is good up to x power 9. So it is very good. I mean, so any polynomial of the x9 it works. So let's compute, do an example. So the code I will show you in a minute. So x squared, you can get exact value 2/3. Of course computer won't write 2/3, SymPy would write 2/3, but not numerical Python. So it gives you a number which is 2/3, a numerical number for 2/3, and is exact for n equal to 2. So but let's compute e to power x. Okay, so let's do that. So there is a small code. So Gaussian quadrature. Alright, so you have to see this bit carefully. So something which I probably didn't emphasize so much, but this is a good line to write from future import division. So 2/3 will be 0.666 with this, otherwise 2/3 will give you 0. So this is something which I did that. Now we are taking e to power x, and I will take the range from -1 to 1, because that is natural for Legendre, but I of course change my range. So how do I change the range? So let's take a small detour. So I want to do the integral from a to b using Legendre, but Legendre is defined only from -1 to 1. Okay, so I make a change of variable. So I'll make a change of variable x prime equal to ax plus b. Okay, so I will demand that when x equal to a, let's not go a to b, because a b is already defined, alpha beta. So when x equal to a, I get x prime is minus 1. So x equal to a gives you minus 1 and x equal to gives you 1. So I can compute alpha and beta easily. So if I compute so what is alpha beta? So let's just so if I just add no, so that's correct. So so you can compute this number, no? I mean, so did I do this way? I think I probably let's just do it here. My notation is slightly different in that note, so I change my notation. So no, so I am choosing x prime. So I've just so let's follow my notes. So x prime is here. So x prime is minus 1. Oh, okay. So x prime is equal to minus 1 when x equal to a. Okay, so in fact it's same, and x prime is 1 when this. So alpha beta will come out to be that, alpha and beta, alpha beta. So my interest is to compute this object x prime. No, actually I am making a slight error, no. So x prime, I think this is this bit of a problem, I believe. So let's just this should be x prime is this is no, this is I have written it wrongly here. Is written wrongly here. So x prime, so this is written wrong. So this is exactly same as is better. So x is variable goes from minus 1 to 1 and this goes from a to b. It's typed incorrectly. So now I can easily solve for alpha and beta. So beta is a plus b by 2 and alpha is a minus b by 2. Okay. So what is the integral? Integral a to b fx prime. This is what I want. So this will be equal to, so I have to replace dx prime by alpha dx, that is a Jacobian. So this is alpha dx, alpha is here a minus b by 2 and this is fx. So x prime, so I have to compute at x prime, which is going to be alpha x plus beta. But you have to compute at those corresponding values, but x will be going from, so this will be lying between, so this will be from minus 1 to 1. So well, I mean you have to map it, appropriately here. Okay. So we can always do it for any interval, but let's focus right now on minus 1 to 1 for e to the power x. So this is the code. So my function is written here. So I am going to use that function and I have to define what is W array and X array. So W array is a weight and X array is a abscissas, array of abscissas. So it's straightforward. So I compute y, which is this function, this one. So first set it to 0 with size, number of abscissas, and I compute y array as f of xi and then sum it up. So this is going to give me the integral. So that's the answer. So for this, my real answer, which is from exact answer is e minus 1 by e, right? Integral of e to the power x is okay. So now I choose my weights. So with 2 points, I am putting my exact values minus 1 by root 3 and 1 by root 3. These are abscissas, and my weights are 1 1. So I also created an array called my error, which has 3 values and my integral, so is going to become clear. So I am going to do for n equal to 2, n equal to 3 and n equal to 4. So I am going to compute with 3 different points, 3 different set of points. Is that clear? So n equal to 2, n equal to 3, n equal to 4, number of points. So that is why I have created my error with 3 entries. So you just look at this line, so my answer is my quadrature, W array and X array and F. So weight, X array and F. So this is my answer. So how much is the error? So one error is my I minus answer, but I want an estimate also from the formula. I didn't write the error estimate. So error estimate formula, if you, yeah, I am sure you don't remember, psi 2n zeta okay. So Wx, I need integral of this, so this product. So this is a error, but it will, so zeta I don't know, so I can get only a bound. So what I compute here is, this is order 1, right, exponential e to power, the derivative of exponential is same. So this is bound with, well, it is bounded from, so we compute this object. So this is a nice feature for Python. So I need to, for quadrature, this is the formula, okay, this is a function, quadrature. So quadrature requires arguments which are, so actually if you may see this here. So quadrature, this function and the limits. So lower limit and upper limit. So this is going to give you the answer. Okay, of course it uses Gaussian quadrature. So I don't know what n is it using. It will choose appropriately, but I mean it don't. It is, if you look at the literature, it will tell you what n is using and so on. But I am not worried about it. It gives me a good answer. But suppose, so f is defined for me is e to power x. But I say, well, I don't really define somewhere else, but I want to just use it in line in the function itself. So the idea is called lambda function. So this is a useful construct. So from here till here to here is the function definition, okay, and these are the limits -1 to 1, and the answer is in 0. So quadrature gives you, so the first one is the answer, the second one gives you the error and so on, it gives you more values. So what is lambda function? So I don't need to get f function entered here, otherwise I have to write this function, all these guys I have to write like this. So you can do in one shot. So it is written here x minus x0 x minus x1 square. So is it clear what it is doing? Is integrating, quadrature is integrating pi x minus x0 x minus x1 whole square. So this line, which is a very compact line, this part of the line is doing this integral, because I didn't need to define the function f, otherwise I have to define another something like here, def f prime will be this function, okay. So lambda function is useful. So I just want to tell you that you really don't need to define, and you need to carry this function, no? I mean right now is part of the line itself. I have to define divide by factorial 2n. So n is 2, so factorial 4. So this is this object without this. So it gives a bound, it does not really give the error because zeta I do not know, but it gives you some kind of bound. So I also print that. So this for n equal to 2, is that clear to everyone? So there is few lines it does it. If I want n equal to 3, then I have to give you 3 abscissors, and 3 abscissors are here minus, square root 3 by 5, 0, square root 3 by 5, and these are the weights, 3 weights. So this from the table. Table has number values, but this I know, I computed them, so I know these values. And again quadrature error will be, but it is x minus x0, x minus x1, x minus x2. So it has one more factor, there is one more factor, because there are 3 points. And my Gaussian quadrature value is here, my I 1. Okay, so I print again for n equal to 3. Now n equal to 4, now I put the numerical values, not, well, this is from the internet. The problem with my table is I didn't put that many digits. So this has something like 15 digits. So double precision as accurate as possible, and you will find this from the net. Okay. So, but you can use my table as well, I mean that will give you reasonably good answer. So this is the abscissas, these are weights, and I do the same thing. Okay. So I get 3 answers and 3 errors. So let's plot them. So we can plot them. So it turns out, so if I just plot them, but I have done some more work. So let's plot it first. Okay, so what we got are, these are 3 lines, my answer is here, well the correct answer is probably this one, my error is here, and so these are some from that column. Okay. So my answer, so we can just check which one is the answer, fine. So I plot the error. Now error looks like this for different n's, 2, 3, 4. Now I plotted it, what scale, what plot is a semi-log plot. So this is linear and this is log. Why did I plot semi-log? If I don't plot semi-log, then it falls like that. Okay, I am not going to do it, I just want to save time, but semi-log it looks linear, right. So I want, linear is something, okay, there is one very important point, I hope it is emphasized in some class. Human beings are very good at identifying linear, somehow it is in our psychology. Non-linear physics problems we can't solve, non-linear equations we have a lot of difficulty, but linear you can see a line is linear. Okay. So linear is very easy to identify. Had it been a line which is going down, so if the line was going down like this, you won't know it is a power law or it is exponential. It's not easy to identify, or it's 1 over x squared, 1 over x cube, but it's straight line, yes, straight line. It's easy to identify. So always go for a straight line. So this looks like a straight line, but I want to fit, is it really a straight line, or is there some correction to the straight line? So Python has a very nice function called polyfit, so polynomial fit. So what should I polyfit? So n is one axis, one variable, so fit you know, no? So you must have done this linear regression, right, y equal to ax plus b, given data xi is yi's, you can make a linear fit. So Python does that within the scene, so we do not have time to get that part, but let us assume that I have set of xi's and set of yi's. So I have 3 points and I want to fit a line with that. With 3 points I can do best is quadratic, nothing beyond, right. With 2 points you can fit a line, and with 3 points you can have one more variable. So I would try both, y equal to ax plus b, actually it is written like this, P is P0 x plus P1. So this is my polynomial. So 0 will be with the highest power, or the second one will be P0 x squared plus P1 x plus P2. I can't fit anything because there are 3 unknowns and I have only 3 points. So best I could do is this. I mean I shouldn't do any other higher polynomials. You have more points than you have choice. So Python will has a function. No need to worry right now how it is obtained, but if you want to read, you can read the literature. So polyfit, but I want in log scale. So I create a log of my error. So this is my y coordinate. X coordinate is n. So I am fitting log of y with n, and I expect it to be linear. So first is with one point with a first order polynomial. So that will be this highest power. So it tells you the highest power. This one means highest power. This is with power 2. So that's why it's power 2. It's exactly same as what I wrote there. Is that clear? Yes. So polyfit will give you a quadratic equation here in terms of n and linear equation here. So I fit both of them. Now this is trivial plot function. So the 2 lines here are the 2 lines here. So polyfit P1 is the red line, and polyfit 2, which is quadratic really, deviates very by small amount, which goes through of course those points, is a green line. So red is as good. So linear is a very good approximation. So what can I claim? I am not doing any mathematical theory, but I can say that error decreases by how much in this scheme? Error decreases exponentially. So these are log plot. So I can claim from here that my error function is e to the power minus n. Can I claim it alpha? So since it is I plotted this, it's exponential. So my function is e to the power minus alpha n. And what is alpha? Alpha is, so I can get what is alpha. So just say P1 I think. So P1 is minus, so first one is P0 is the slope. Okay. So P0 is minus 5. P1 also will be, P2 also will be similar. P2 is my variable, okay, I stored them. So minus 3.16. So this is the linear coefficient of linear plot. Okay. So I can't really put my, I mean I won't bet on this number minus 5, but it's linear with minus 3, minus 4. Okay. So I can claim definitely that error goes down linearly. So this is about Legendre polynomial. So I can use Legendre polynomials to do Gaussian quadrature. If I want from not minus 1 to 1 but some other points, then I use this scheme to get my answer. Okay. I have to compute this function at rescale values. Okay. Now this is about Legendre polynomial, but we can do more. So let's just use this slide only. I mean I'm not going to write those functions. So we encounter these kind of integrals. Okay. Now I want to integrate this integral. So of course is no good idea to use the Legendre for this because infinity is coming in here. So can you make a guess what basis function should I use, or what polynomial should I use? Ligor polynomial, which is done for hydrogen atom. So hydrogen atom, if you recall, plus the V minus R like this. Okay. So Ligor polynomial is a good choice and it has very interesting set of properties. So is exactly same scheme, but my weight function, this now you can see that here weight is not equal to 1, and this approximated as Wj Fxj. So my weights will be computed from Ligar polynomial, and my xj's will come from the zeros of the appropriate Ligar polynomial. Okay. Now the derivation, somebody has done it already, we do not need to compute this, but given n, I will give you xj's and I will give you wj's. Okay. So I have put down some notes. In fact, those polynomials I am I am not afraid, but they are very kind of, it's quite, I won't use the word clumsy, but like that, just lot of algebra. How many of you like them? Nobody likes them, but they are very powerful, okay, that much I can say. So you should know how to use them, and I am not very comfortable with them because I do not remember all the recurrence relation. So we can get, this is formula for the weight, this formula for weight. So given the Ligar polynomial, you can compute the what is the weight, and also the abscissas are obtained by the zeros, and zeros, of course, how to compute zeros I have not told you. I am not sure whether I will have time, but there are methods to compute zeros of a function. Okay, Newton was one of the person who gave us this scheme. So there are clever schemes to compute zeros, but let us assume that somebody has done it already. So these are the table. So one thing is to know how to use them, okay, that is something which I would want you to learn from this discussion. So these are my two abscissas for n equal to 2, and these are the weights. So now they are not, there is no symmetry, there is no, in fact minus values do not even exist, r is always positive. So we will have n equal to 3, then this thing, this. So there is one homework, so solve for hydrogen atom. So hydrogen atom, you have the wave function. So some people are from different department, but quantum mechanics you have done it already, but you do not need to really go back to your quantum book if you do not want to. If you want to, of course, go back and look at it, it is more useful. So given the wave function, I only do the radial part, I am not worried about the theta and phi part, because I give you only m equal to 0 and l equal to 0. Two quantum numbers are 0 zeros, the what is called azimuthal quantum number and magnetic quantum number. So they are set to 0. In fact, the homework is here. So this is one of the hydrogen wave function. So this is my f of r, or if I want mod square, then I have to square them, but it is again f of r. Okay. So you play around with it, and no, actually f of r won't be that. So sorry, f of r will be what is f of r? So let us say I want to compute mod psi squared dx. So just to do the exercise, I am interested in mod psi squared d vector r, integral 0 to so over whole volume. Right now I can't put the limits. So there are factors in front. A is the Bohr radius. Okay. So factors in front, let us call it alpha squared. Inside will be the one r dependent is 2 minus r by a whole squared exponential minus r by a. So I square it, so r by a. So this dr integral is volume integral dr, and so there is a d cos theta d phi. So I have d phi and this d cos theta d phi. So this gives you, since there is no theta dependence and phi dependence, this gives you 4 pi. Okay, 2 coming from here and 2 pi coming from here. So I have to do this integral. So somebody told me that you can use these formulas. So this will correspond to that and fx will correspond to this. Okay. So I have to compute this function at the abscissas. So you are basically left with dr integral with 4 pi coming outside. Now my strong recommendation is get rid of a. So how will you get rid of a? So r by a is equal to r prime. So I divide by a, multiply by a. So a will come out of here. So a comes out here. Now this is a number 0 to infinity. This has no a dependence, right? So this is, so I can write this as 0 to infinity 2 minus r prime exponential minus r prime dr prime. This is more convenient if you use these formulas because you will get number, you will not get a length dimension in the mathematical formulas. So exponential of 1 is a number, it is not 1 centimeter. Is that okay? So in all the math formulas we have exponential takes only a number, exponential does not take 1 centimeter. You always are dividing by some unit. So this is what you should compute from here. So this I will leave it as an exercise, you must do it and you should get an answer 1 for this. Now this a looks like the mod psi square has a dimension of a, is that correct? So this should be number 1. So this a must cancel with something. So where does it cancel with? So alpha squared has very rightly, so a 3 by 2. R squared, yes. So we made a mistake. So r square dr, it is not r dr. So the r square dr, so in fact I should get rid of, put a cube outside because I have to divide by r by a whole. Okay. So now this guy is cancelled dimensions. So this is another way to check whether I am doing it correctly or not. So I need to compute this object r prime squared. Okay. So that is how you, so this is a very standard stuff, but it is always a good idea to get rid of quantities with dimension. So this is a very nice book in math methods. You are aware of this book, Matthews and Walker? Okay, this is my favorite. So Matthews and Walker, math methods, he does quite a bit of integrals, with quite nice discussion on that. Now this for hydrogen atom. Now we can do the similar exercise for oscillator. So oscillator, what does the corresponding formula look like? Leguerre. So the Leguerre-Gauss quadrature. Now for hydrogen atom I get the formulas of this sort. So I should choose something which has weight function like that. So this is weight function. In fact, if you look at Hermite's polynomial, the orthogonal relation is e to power minus x squared hn of x this goes from minus infinity to plus infinity. Okay, and there is a factor in front which I do not remember. Okay, so this is a orthogonal relationship for Hermite's polynomial and this is appropriate. So my function f of x should be expanded with this. Somebody may say why not expand this, but it is not a good choice to expand e to the power minus x squared minus infinity to plus infinity, that has very high order polynomials. So you should, so you want a good answer, then my f of x, you see it is really, for this case is cubic. So for hydrogen atom also this f of x will be small order polynomial and you will get a very good answer if you use f of x as a superposition of Hermite's polynomial. So this object is again same formula Wj fxj. Now my abscissas are zeros of the Hermite polynomial, appropriate Hermite polynomial, and weights are computed again by somebody has done it already. Okay. So this is how we compute for a hydrogen atom, and so just for completeness I can show you that. Okay, so this is a wave function psi 0. Now it has exponential minus y squared, so which is similar to this. So if I square the wave function, then I will get exactly this, but y is already dimensionless, and y comes as x by alpha, and alpha is that quantity with dimension. Okay. So you can use Hermite polynomials for integrating hydrogen atom wave function and quantities related to it, and so I will leave this part of how to do it. So zeros are given in the table. These are the zeros for Hermite polynomial. These are symmetry now, again plus minus symmetry. So for n equal to 2, these are 2 values of abscissas and weights, 3 values of abscissas and weights, and like this. Okay. So again you should do for n equal to 2, 3, 4 and see how the error drops with n. So this is called Hermite Gauss So I have bit of time, so let me also show you how to use a special function. Okay. So you have to import from SciPy special. Okay. So this is what you need to import, special. Now this for Legendre. So special dot Legendre with n will give you this Legendre polynomial. Okay. So I can just play around with this. So by the way, this will give you polynomial, it doesn't give you numerical value, and you can compute at any value you like of that polynomial. So let us just play around with it. How does it give you? So special is for special function. Okay. So let's copy this. So LEG equal to special dot. So I want second order polynomial phi 2, I believe. So LEG, how does it look like? So this gives the coefficients. So it gives you that. So these are the coefficients, minus 3 half, 0, minus 3 half, minus half. So remember what was it? So Legendre 2 is 3 by 2 minus, so what is 3x squared, so it tells you that 3x squared minus 1 by 2. Okay, so you can construct from here. So 3x squared, this is 0 minus half x, sorry, no, minus half, no x, minus half. So 1.5 x squared minus half. We can do for even, so Legendre, let us say 3, so it gives you 2. So it is a 5, so 5x cube minus 3x by 2. Okay. So this is what I did here. I wanted to plot, so I need numerical values. So I put a lin space. Something has happened here. So I compute y, array y with lig x and plot. So this will plot all of them in one loop. So I go from 1 to 5. Okay, I didn't do 0, 0 is flat, so 0 is not included in that plot. Okay, so you can also play around with spherical harmonics. So this was spherical harmonics part, but there is nice plot, I have commented it, but you can play around with it. Okay, so this is my discussion about quadrature. So I am going to skip. So there are several other ways to integrate. So there are functions which are more complicated. I am skipping that part, like singular functions, how to integrate, that I will not do in the course. We can also use random numbers for integration, that I will do later. Okay, and there are some nice iterative procedure to integrate to get accurate answer, that also I will not do now. So next class we will do differentiation, and then we quickly go to ODE solvers. So I want to kind of cover ground so that you can start your project. So next class is differentiation on Friday.